Okay, I think this is actually going to be a pretty short video. There's not a ton of stuff to go over here. Rick is going to be talking about analyses on categorical variables this week, basically running crosstabs. So the first thing we're going to do is install some new packages. We're going to be using this gmodels package and this package called mass. So you'll want to run these first two lines. I'm not going to do that because I've already done it. And then you're going to want to open all three of these libraries so you can import your data set and then run the other analyses that we're going to be doing later on. And then don't forget, you're going to want to obviously update this to whatever your most current version of your data set is and import your data. Now we're going to be working with a variable for party ID in the next assignment. So, and right now we're just keeping it at a 3-level party ID, just Democrat, Republican, and Independent. You might actually have some 5s, which is other party, and then there's a blank for them to specify. You'll probably for sure have some -9s, and then potentially you could have some -8s or -4s, or 0s even. All of these we're going to lump into NA. We're just only going to label the Democrat, Republican, and Independents. And everything else is going to go into that NA catch-all. For now, we'll recover some of these observations later when we recode this in combination with another variable to make a 7-level party ID. So we'll take a look at the data first. And you see, like here in my data, I do have some 5s and I have the -9s. But these 3 levels here are the ones that we're going to retain. This is just, a simple if-else function, 3 of them nested within each other to label Democrat, Republican, Independent. So this is going to be a nominal variable, and we're going to actually label it with the words Democrat, Republican, and Independent. Later on, when we do the 7-point variable, we're going to keep it as numeric. That has some advantages when you start running other types of models. So if we run this, see it, the recode worked. And then we're also going to, because R likes to alphabetize everything, and it actually truly doesn't matter in this case because Democrat, Independent, Republican is in alphabetical order, but I don't know, for some reason I decided I was going to make this a factor variable here last year. So go ahead and run this code too, to put what's already in order again, and then run another table, and just double check that you've got everything matching. So 1 was Democrat, I have 417 of those. 2 is actually Republican, I have 380 of those, and 3 is Independent, and I have 358 of those. And the 5s and -9s disappeared into the NA category. And this is something that I actually have not, I don't think I've mentioned this yet, but it's a really good practice to include spaces between characters and operators. So in between, like, here and here, to make sure you have spaces. This makes your code look cleaner and nicer, but also can prevent some errors. It can prevent our from becoming confused in a situation like this one here. So in the first situation, it's very clear that you're saying the variable, whatever this variable is less than -9. I don't know why I had greater than. But in this case, it's hard to tell if you're saying that this variable is less than -9, or if you are trying to assign the value of 9 to the variable, because you see now this less than sign and the negative sign are smushed together, and it kind of looks like the assignment operator. So just best to clearly put spaces between all of these things. Okay, so homework 3 is going to ask you to run crosstabs, showing the proportion of each respondent in each party category who fall into each category of several policy variables. So you can actually create a contingency table using the table function that we've already been using to look at the data by just adding a second data or a second variable with a comma between them. So whichever variable comes first, if you want to, I've got it assigned to an object here, and then if we just run the object, it'll make the table appear down here. So whichever variable comes first is going to be the rows, and whichever variable comes second is going to be the columns. So now you see how many Democrats feel whatever one was about abortion. I think one was, well, we had the low values being liberal, so I would say one is people who think that Democrats who think that abortion is fine in all circumstances or whatever, and so on, into the other categories, and then the other parties. Crosstabs also includes several other measures, which you'll learn about next Tuesday in class. Here are some of the things that it tests, or here are some of the tests that appear, or the results from the results appear in the crosstabs. One is a chi-square test, and the base R function for that is just CHISQ.test, and then your object in the parentheses. This has to be, I think this has to be a table. It can't just be a variable. So, and I don't think you can put this in there either, but don't quote me on that. I think I might have just put it in here to make it easier. So anyways, running that will give you this information here, which will make sense to you again after next week's lecture. And then if we create an object for this test, we can then look at the attributes and extract any that we want. So the attributes are, it has two. Names and class. And what we're actually looking for is this here, the expected values. Because in crosstabs, we get not only the actual values that fall into each cell, but another thing that's important in calculating the chi-square is the expected values. So we can actually extract those like this into a table here. So now we've got the expected values, and we've got the actual values. And if we wanted to, we could do a bunch of merging and create a table with all of that data in it. But of course, this is R, and there's a package for that, so that we can do it all really easily, which we'll get to here in a minute. Here is a different variable that we're going to look at. This one is the question about the income gap, how people think about the income gap. So here is a contingency table. And then we're going to run the chi-square test on that, which is going to actually give us a warning. And so we'll do a few more things, and it'll tell you why it's giving us a warning. So we're going to look at we're going to do these steps again to get an object of that's chi-square test, and then pull out the expected values. And we see that for the value of 5, the expected values are less than 5, which you will learn in class. Next week is a red flag for you shouldn't be doing a chi-square test in this case. So I think I don't remember if Fisher test is an alternative to a chi-square test or if it's just another test. But here's the code for that. But the problem is our computer is not big enough to handle this computation. It's designed for a 2x2 contingency table, and we're looking at like a lot more categories here. So it needs a lot of computing power to produce results. This error warning tells us to try to increase the size of the workspace. So that's what this extra argument in here does, which now produces another error telling us that the workspace is still too small, and it suggests that we allow simulation of the p-value, which relies on a Monte Carlo situation, which you're not probably going to know what that is, but it doesn't really matter. Here is the code to do that. And it'll actually spit us out some info here. Now, like I said, there's a shortcut so that we don't have to do all of these tests separately. And it is actually one that you can find in the text. It's this function called Crosstable, which I think this came out of the mass package. So the function is Crosstable, and then similar to up top where we were putting the two variables in separated by a comma, that's your initial argument. So X is going to be your PID 3 and Y is going to be abortion. And then digits is the next argument. You're going to feed it however many digits you want it to round the output to. Chi-square test equals true. You're telling it to calculate the chi-square test. If you just leave this off, the default is false, so it will not give you the chi-square test. So you need to add this argument here. And then expected equals true. I'm not sure what the default is on this, but if you can set it to false so it doesn't give you the expected values, or set it to true so it does. And then also it will give you the standardized residuals. And then there's this last argument, format equals SPSS. This puts it in a nice little table that looks like the output from SPSS, which is Rick's favorite. So that's what we do. So if you run this, you will get this nice looking table that has all of this information in it. So this tells you, this is kind of a label for what each of these values in each square is. So here's your count, your actual count. Here's your expected value. And again, you'll understand the expected value business more after class next week. This is the chi-square contribution. So I believe if you add up all of those, you get the total chi-square for the entire model. This is the row percent. So if you add up these going across, these four should add up to 100. This is the column percent. So again, if you add this and then this one and then this one, they should add up to 100%. And then this is the total percent. So like if you add up these in all of the cells, it should total 100. And this is a standardized residual. And then of course you got row totals over here. So this should theoretically be all of these totaled up. And then this should be, if you add these three, these should be 100. And same with the column totals. This should be a total of all of these. And then if you add these up, it should be 100. Chi-square for the whole thing is 265 with p-value 2.37 and a bunch of numbers to the negative 54th power. So this is a significant chi-square test. Again, more on that in class when Rick lectures on the actual statistics behind all of this code. Okay, so let's pull this down because there's just a few more things that he will touch on. This is going to even be a more basic explanation. I'm just going to explain the code here to you and the packages and stuff. I'm not going to try and explain to you what all of these things are. They are called pre-statistics. There are other, I think there's other ways to find these, but last year when I went hunting for how to calculate them in R, these seemed like the ones that worked the best. You don't use these very often. I have like never used them outside of this class, but you never know. It depends on what kind of data you're working with. So it's still good to know. So anyways, they are in this package called Desk Tools, that if you haven't already installed it, go ahead and do that and then open the library. Did we do that at the top? No, that's a new package. So yeah, you're definitely going to need to install this and then open the library. And then there's 1, 2, 3, 4. There's 5 PRE statistics, pre-statistics that Rick will talk about. One is lambda, and there's a few different ways to calculate lambda. So there's this function. It's all the same function, but then it just depends on what arguments you add to it. So if you just do the 2 variables that you're working with, it's going to assume it's symmetrical data, and average some stuff. I don't remember what this all is. You'll learn that next Tuesday. But if your data is either column dependent or row dependent, you need to add this additional argument at the end. And it's super backwards because, of course, why wouldn't it be? And if it's column dependent, you add the argument direction equals row. And if it's row dependent, you add the argument direction equals column. My notes say that we want column dependent since X is party ID and Y is abortion. I don't remember why that is, but if that's what I wrote, I'm sure that's correct. And we'll be able to explain to you why that is on Tuesday. And then there's these 4 other statistics and so there's 4 other functions: Goodman Kruska gamma, Kendall tau B, Stewart tau C, and Summers delta. And it's all the same thing. It's just the function, and then in the parentheses you're going to have your 2 variables separated by a comma. So you can run all of these if you want to. None of the output is going to mean anything to you, but you might want to run them just to make sure that your stuff is working, so that we can troubleshoot in class if it is not. And then, it's going to spit some numbers out. That you really don't know what the hell they are. So there you go. And then I have this question: why would this be inappropriate? So I guess we'll figure that out next Tuesday. And that's it.